Okay, so just to say it again, the linearized Franz-Well theory we can write in terms of a whole new set of fields. So when you go to the frame formulation, basically you have a whole new set of fields which have the symmetries of a Young tableau, two-row Young tableau with S-1 indices, and T which can go from 0 to S-1. T equal to 0 is your original frame index, and the higher one, the T equal to 1 is, if you wish, the generalized connection, but the higher T's are something called the extra fields. They are effectively auxiliary fields which are necessary just to recast this whole thing in a more gauge invariant fashion. So these extra fields are determined effectively by this generalized torsion condition in the same way as the connection field is determined in terms of the field bound by the in general relativity by this condition. But this way of rewriting the dynamical equation is maybe a little more unfamiliar, but it's, as I said, the generalization of putting the Riemann tensor equal to the wild tensor. But here, let me explain a little bit what this generalized wild tensor is. So it's something which has S indices. It also has the symmetry, so this is the C, and it's it has S indices on top and bottom, because you see there's a S-1, and then there's an additional C, and this comma separates the two sets of indices. So this is all symmetrized, this is all symmetrized, and mutually antisymmetric, like in a Young tableau. So you have this generalized wild tensor, but this generalized wild tensor is not arbitrary. It's constrained by a Bianchi identity. So like the ordinary wild tensor also obeys a Bianchi identity. But other than that, it can be anything. So if you wish, it's setting the, so you have an arbitrariness in your CABCD, in the case of Einstein theory, up to the freedom, up to the constraints of the Bianchi identity. But you could put it to anything and you would get a solution of the Einstein equations. And so to capture this feature in this more general frame-like formulation for these higher spin fields, Vasiliev took the sort of next step of introducing the so-called unfolded formalism, which at first sight will seem extremely baroque because you express the equations of motion in terms of a constraints on an infinite number of auxiliary fields, which in a way is what we are doing even by rewriting the Einstein equation in terms of the wild tensor equal to the curvature tensor. We are sort of writing it more like a constraint equation, and this will be sort of taken to its logical extreme. So to illustrate this unfolded formalism, let me tell you what is the most complicated way of writing the free Klein-Gordon equation. So if you're interested in massless scalar fields which satisfy just del square C equal to 0, one way of capturing the information about the Klein-Gordon equation is to introduce an infinite number of fields and write down an infinite number of equations for them as some kind of constraint equations. And the way you do it is define fields C A1 to AN, symmetric traceless zero-form fields, and you define a chain of equations between them. So the first one is, so you have n goes from 0 to infinity. So you basically start with Young tableau with n indices. So you have fields C A1 to AN. And the simplest one is just without any index, so n equal to 0 as well. And you impose this kind of an equation which is which relates the case with n equal to 0 to the case with n equal to 1 by in this way. So dC is E bar wedge C. CA, and then you write down the next. So C, this is relating the 0, the case with n equal to 0 to the case with n equal to 1. Then you have the next element in the chain is relating the 1 with n equal to 1 to the 1 with n equal to 2 by something very similar, and you go on in the same way. dC of A1 to AN minus 1 will be E bar C, wedge C of A1 to AN. So you can view this chain as simply definitions of the successive derivatives of C. So for instance, you can view this as defining CA in terms of dC. Basically, it's saying that CA is the derivative of C, the first derivative of C. And this tells you that CA12 is the second derivative of C. I mean, it's equal to the first derivative of CA1, which is in turn the first derivative of C. So basically, it's saying that CA12 is the second derivative of C. But then the tracelessness of this, which is consistent actually with this equation, tells you that, so if you look at eta A1, 2, so basically you contract these two indices and set it equal to 0, that effectively tells you that the second derivatives of C obey this equation. So the tracelessness, it gives you the equation of motion. So in a way, and then all the other derivatives do not, they just follow from taking further derivatives of this. I mean, the additional constraints are just further derivatives of this. So in a way, what you are doing in this unfolded formalism is writing down a set of constraints for this, for the different derivatives of the fields, and imposing the equation of motion sort of by just some kinematic kind of constraints like this. So this is something, I mean, it's not the most obvious or intuitive way to do things, but it's certainly a way, and you can do something similar with ordinary gauge fields and spin 2 fields, also using the Bianchi identity. So for gravity, the Bianchi identity would tell you that the covariant derivative of this R, so since R is related to the Weyl tensor by the Einstein equation of motion, the covariant derivative tells you that the left-hand side must be 0, therefore the right-hand side must be 0 as well. This is the statement about the Weyl tensor obeying also the Bianchi identity. But in this language, you can phrase it in the following way, that the only way in which one way in which you can satisfy this Bianchi identity is if you choose this dC to be some linear combination of arbitrary fields with now 3 indices. So we started for S equal to 2 with a Weyl tensor which had 2 indices, CAB, CCD, but demanding that it satisfies the Bianchi identity just tells you that this dC can take this form where the CACF are generally arbitrary. So they are things with 3 boxes on top and 2 boxes in the bottom. So you can think of this as basically a way of parametrizing the first derivatives of the wild tensor, and you can parameterize in terms of tensors obeying these symmetric, this property of these Young tableaux. So these C's parameterize the non-vanishing first derivatives of the wild tensor, but they are not completely arbitrary either, because you have a further Bianchi identity, essentially like d square equal to 0, which gives you a constraint on the C's. And one can follow this chain, like in the case of the scalars, and write down a chain which says, the chain of equations, which relates the kth derivatives in terms of the kth derivatives with the k plus 1 derivatives. So this with fields, so you have basically you now have something which has k plus 2 indices and 2 indices here. So you have Young tableau of this kind, because the most general solution of this chain of Bianchi identities are parameterized in terms of Young tableau like this. So, so basically, it's a more complicated version of what I wrote down with the scalar field, and it's the unfolded version for the spin 2 field, namely a way of parameterizing the most general solution of the Einstein equations, at least at this linearized level, in terms of a whole set of auxiliary fields carrying this symmetries. Auxiliary fields labeled by two row Young tableau with k plus 2 boxes and 2 boxes k plus 2 in the first row and 2 in the second row. And so this was generalized by Vasiliev to higher spin, and we have this generalized wild tensor which appeared so this generalized wild tensor here had S indices, so this was the usual C, A, B, C, D, the usual wild tensor, but for the spin S, you have this is the basic wild tensor, but you have once again the Bianchi identities for which the linearized curvature tensor obeys, tells you that that you can rewrite a chain of equations which relate this to now more general fields which have k plus s boxes here and s boxes here. So that's the generalization of this case where you had k s equal to 2, where you had k plus 2. So you had k derivatives of the original wild tensor here, you have k derivatives of this generalized wild tensor, and you have a chain of equations consistent with the Bianchi identity. So the linearized Franz-Stahl equations, which were fairly straightforward and nice, can be written in this horrendous way in terms of 2 infinite set of equations, one of which, just to write again, one of which is the generalized torsion equation for the curvature, generalized curvatures. These are when t is less than s minus 1. For t equal to s minus 1, this generalized curvature is not 0, but related to a generalized wild tensor, and the generalized wild tensor can be parameterized in terms of its derivatives, which obey this chain of equations. So the claim is that the Franz-Stahl equations are equivalent to this set of equations for now 2 sets of fields, namely these omega fields, which, so just to, let me put it up on the board somewhere. So you have two sets of fields, these omega fields, which contain, for a spin S, they contain S minus 1 boxes here and P boxes here with, for any given spin S, you have these connection fields, and 0 is less than equal to T is less than equal to S minus 1. That's one set of fields. And then you have the C fields, which are parameterized also by Young tableaus with K plus S boxes and S boxes, and K is equal to 0 to infinity. Okay, so that's the set of fields, and so it's just a way of introducing many auxiliary fields and writing the set of equations. Okay, so that was already quite, so the linearized theory was already fairly complicated in this form. But to write the nonlinear theory, it's useful to go to a spinor basis. So these were tangent space indices. The ones A1 to AS minus 1. These are tangent space indices. So instead of the tangent space, at least for d equal to 3 and 4, you can write in terms of spinor bases. So for instance, we know any vector can be written in terms of two spinors, a dotted and an undotted spinor in 4 dimensions. In 3 dimensions, we just have one kind of spinor is sufficient to write down a vector. There's a polymatrix going between them. So you can rewrite all these fields which have various tangent space indices. You can rewrite them in terms of the spinor basis, and basically for a tensor with P indices and Q indices, you can trade it for something which has n dotted spinor indices. So we'll stick to d equal to 4 for the time being. And m undotted indices, where it's easy to see from the Lorentz transformation properties, given that these are completely symmetric in this way, in this Young tableau way, that the spinor automatically takes into account the tracelessness and symmetry if we have n spinor indices and m spinor indices, where P and Q, the number of indices, are related to the number of indices here in this simple way. So these omega fields, the connection fields, you can write for spin S in terms of some in this basis, but now with n plus m equal to 2 times s minus 1, because the top row is always s minus 1. N minus m will be equal to t, 2t. And these other set of fields, again, go to the spinor basis, and you have n minus m, which is the bottom row, is 2s, but n plus m is the top row, is 2 times k plus s. Okay, so that's a convenient thing to do for some reasons which will become clearer in a moment. So now the thing that, so far we did, everything that I said was true for spin by spin. For each spin S, I can do this, the Fronsdal equations were like that, and this Vasiliev reformulation was also that the different spins didn't talk to each other. But in the nonlinear theory, we want them all to talk to each other, so that's why we'll put them all together now, but yeah.
So in the free field theory, is it known how to solve the constraints to write an action?
I'm sorry?
In the free field theory,
yes.
Is it known how to solve all of these constraints to write an action in terms of all of these auxiliary fields?
Yeah, so in the free field theory, yeah, you can write down, because essentially it's a quadratic action and you can write them down. There's actually a simple dictionary which I did write down between the Fronsdal fields and linearized so you take this field E mu A1 to AS minus 1 and contract it with the background Vierbeins, and you get the linearized Fronsdal field. So you can go back and forth between the Fronsdal field and the spring fields at the linearized level. But beyond the linear level, it's not really known. Okay, so as I said, we will package them all together. This is very much like how you work in superfields. When we write down in supersymmetric theories, we put together all the fields which transform under the supersymmetry into one superfield. This is something very similar, except that now you have an infinite number of spins. So you write down a superfield in which you sum over S and you take, let's start with just these omega fields first. So this omega fields which have indices, n indices, beta undotted indices, and m dotted indices, you multiply them by Grassmann even spinor oscillators, so commuting spinor oscillators. So y beta 1 to y beta n and y bar delta 1 with the dotted indices, and you sum over all n and m. Basically, I've chosen to write the sum over n and m in the following way. You sum over the ones for the given spin. Those are the ones with n plus m equal to 2 times s minus 1, and then you sum over all s. That's equivalent to summing over all n and m. So this is just a way of packaging all these fields into a large superfield. In the case of supersymmetry, we normally work with anti-commuting spinors. So that's why this truncates up to some maximal spin. But here we work with commuting spinors, so you have an infinite number of them. So there are some parallels with supersymmetry as well. The way the higher spin symmetry acts is more natural in terms of these, in this superfield, which now depends on this capital X will denote my space-time AdS, space-time variable, and these Y's will denote these Y and Y bar collectively. So you have a superfield which is a one form, because this is a one form. It has tangent space, coordinate space, one index. So we keep that all through. So you have a connection superfield which is a one form. Any questions? Okay, so and we do something similar for this other set of fields, the C fields. Again, we sum over all the Y generalized Y tensor fields with different n and m or different s, and we define a Y tensor superfield. This is a zero form. This does not. There shouldn't have been any alpha here. This doesn't have any. So there's no alpha there. This is a zero form in space-time. So you say the Y's are oscillators, they commute. The Y and the I think I've written down the oscillator algebra in a transcript. I should say that when I say they don't commute in the sense, they are Grassmann, so they anti-commute. But what I mean to say is that they are Grassmann even, in the sense that in the sense that you have so they are bosonic variables, but are bosonic variables which carry spinorial indices. So they transform under the Lorentz group as a spinor, but they are bosonic. It's also convenient to define certain derivatives like the superspace derivatives. One defines a slightly different form. These are not indices. This means adjoint. So this D is the ordinary covariant derivative, and then there is an additional piece involving the oscillators, and this D tilde is another combination, and both of these obey some relation like this, and the linearized curvature can be written very simply. The linearized curvature that I wrote down earlier in terms R in terms of the connection can be written essentially in terms of this operator. So already this repackaging makes things a little simpler. And then all these linearized, the set of equations that we had in this unfolded formalism written in terms of the superfield can be written in the following way. So remember, there was one set of equations which told you how the curvature defined in terms of these omegas. There was a piece which was the torsion piece, and there was a piece related to the Weil tensor. All that is, both those set of equations are packaged into this. So basically, this is saying that this R, which is in general a function of y and y bar, is the sum of a anti-holomorphic and a holomorphic piece. So that sort of captures the fact that most of the components are 0, except for some. So if you set the y oscillators to 0 in C and take the derivatives with respect to y bar, and these are the background Vierbeins written in terms of the tangent indices, and then this is the first linearized equation, and then the equation for the Bianchi identity can be written in this more simpler form, this d tilde of C equal to 0. Basically, that sort of expresses the Bianchi identity. So these are the linearized equations in this unfolded formalism. You can sort of package them in a more or less compact way. But we want to go beyond these linearized equations and write down the nonlinear equations. So that was the whole point of going through all this reformulation. So to do that, we use this higher spin algebra, which is the analog of the supersymmetry algebra with these bosonic kind of commutation relations for these oscillators. So if you consider the oscillators defined, so if you wish, these are sort of operator valued oscillators satisfying these commutation relations, then these oscillators actually are the familiar way in which some of you may recognize how you can capture the AdS algebra. The O3, 2 algebra can be, there's an oscillator construction in terms of quadratic combinations of oscillators. So these are essentially so I've written it in a form which is like that of the Lorentz group, except that the commutators will be slightly different. These are the analog of the translations, and these are the analog of the Lorentz rotation. There is another one which has both dotted indices, and this one has one dotted and one undotted index. So this is this is independent of any of this. You have this oscillator construction of the O3, 2 algebra, and but the higher spin algebra is a generalization of this O3, 2, in which you work not with just the quadratic combinations of y, but this more general set of elements which involve sort of n y's and m y bars, and consider this this has some basis, and this forms a basis of the higher spin algebra n equal to 4, with n plus m equal to 2s minus 1. This will be so in the case of s equal to 2, you have n plus m is equal to 2, and that's what you have, one dotted, one undotted, or both dotted or both undotted. Those are the spin 2 or the generators of the tangent group. But this is a more general set of generators, and they generate an algebra. When you do the commutators, they close, and you can sort of convince yourself that the commutator of a spin S1 generator and a spin S2 generator will give you a set of generators whose spins will go between some limits. And you can see that the moment you include S equal to S greater than 2, this will not truncate. It will, you need the whole set, because for this simple reason that for S1 and S2, one of them greater than 2, you get something. So for both of them, say S1 equal to S2 equal to 3, for instance, you'll generate a spin 4, and so on. So that's the higher spin algebra. That's just an algebraic statement. But that is the symmetry, that infinite dimensional group is the symmetry that will underlie this nonlinear Vasiliev theory. In some ways, that's the whole point. I mean, that was the thing that Vasiliev exploited to write down the nonlinear equations, because he now could use that to write down non-abelian field strengths, which would have this kind of form, the omega plus omega star omega, where the star is essentially a way of capturing the oscillator products. It's a kind of Moyal product. Those of you who have seen the non-commutative Moyal product will recognize this form. It's essentially very similar. It involves e to the derivatives but now on the y's and y bars, acting on the left and on the right. So this is a way to write down something covariant under this oscillator algebra. But the next step, which I don't have much of an intuition for, is that to write this full nonlinear system, you have to introduce yet another set of oscillators and another superfield. So you introduce another set of oscillators, Z and Z bar, and now you promote and you introduce a new superfield which depends on the Z oscillators as well. And moreover, there are sort of one forms in this oscillator space. They carry, if you wish, one form. They carry spinor and spinor indices. And moreover, these omega fields also need to be promoted to fields depending on both oscillators. So you have many more components. If you set Z equal to 0, those become the original fields omega. Similarly, the C gets promoted to another field, which again, at Z equal to 0 is this original field. But for Z not equal to 0, you have many more auxiliary fields. And this Y's and Z's also obey this oscillator algebra and a star product. And in terms of this, the gauge symmetry acts linearly. You can define as a gauge superfield, a gauge parameter superfield epsilon, which when acting on this field W transforms like a gauge field does. So you recognize this as the sort of linearized gauge transformation, and this S transforms as if it is in the adjoint representation of S, and this B is what is called the twisted adjoint representation. This pi is, I'll define this pi operation in a moment, but you can write down now the full nonlinear Vasiliev theory in some relatively compact form. If you define this curly A to be W plus this new field S, then the field strength of A is more or less non-zero except for some pieces which depend only on this dz bar. This K is a particular, it's not a field, it's just some combination of oscillators which plays a certain role. And this pi is something that just flips the sign of the y and the z oscillators without doing anything to the y bar and the z bar. So you can write down the full nonlinear Vasiliev theory in terms of this set of equations, one set for this W and S, and another for B. So this B transforms in some kind of an adjoint representation. And so that's the sort of form that Vasiliev dreamt up, which satisfies the full nonlinear gauge symmetry and is consistent. So there are various consistency conditions like a Bianchi identity, etc., and you can show that those are obeyed. In fact, the right-hand side can be written in a slightly more general form. It can be any function of B star k. Here I've chosen this function to be linear, but one can show that by field redefinition, the most general form it takes is where f of w is of the form w times, so it's a linear function times exponent a pure phase e to the I theta of w. But if you demand that this theory has parity invariance, this theta can take only two values, either 0, in which case f of w is equal to w, which is the case I've written here, or theta is pi by 2, in which case you get I, and you can put an I over there. And these two are what are called the type A and the type B Vasiliev theories. But if you, so this, by the way, I should say, this is in the 4-dimensional case, and the 3-dimensional case is very similar. There are some simplifications, and we'll come to that later. But if you allow parity to be broken, and we'll see reason why that might be a good thing in AdS 4, then you can have a more general function of W. But we will mostly stick to these two cases. And of course, these nonlinear equations are designed in such a way that when you linearize around AdS, so the AdS vacuum consists of some particular configuration of W and B, and when you linearize around that, you get the linearized Fronsdal equations in this frame formulation. So this is sort of just a rapid sketch of the Vasiliev formulation. So I don't expect you to have absorbed everything, but I hope you got a picture. Any questions? Yeah.
So in the case of positive plus one constant, what would be the main difference?
In the case of?
Positive plus one constant.
Oh, not a big difference. I mean, basically lambda goes to minus lambda. So lambda, in a way, has been set equal to 1 in all this, but otherwise, I mean, you can put back lambda by scaling your oscillators, because the oscillator algebra, that's what gives you the AdS isometries. you can put a lambda over there and take lambda to 0. You get the Poincare group from the AdS isometry group. So you can rescale your oscillators and put back lambda, but you will see there are inverse powers coming in many of these places. So lambda to 0 is singular, but lambda to minus lambda is not a problem. In some indirect way, in the sense that the Moyal product, remember, acts only on the oscillators. It acts on the y's and the y bars, not on the space-time, not on x. So it's not a non-commutative theory in the space-time. So I should have stressed that. It's not non-commutative it doesn't have a star product in space-time. It's more in this oscillator. I mean, it's more a trick for capturing the oscillator algebra. But indirectly, in a sense, it feeds into that because basically where it comes from is from this infinite chain of equations. So you can, the fact that you have these connection fields are arbitrary, you have this whole tower of these connection fields, means that you use this generalized torsion equations to solve for a lower field in terms of a higher field, and so on, work your way back to the Vierbein, just like you do over here. But we know that omega, when you solve, is related to, when you solve this equation, omega is related to a derivative of E. But when you do this here, the higher omegas are related to derivatives of the lower omegas. And then, so when you go from the big one to from many boxes to no boxes, you have that many derivatives. And then you have arbitrary spin, so you have things of arbitrary many derivatives. So that's roughly the reason why you have a non-locality. But it's packaged in this way, in this oscillator construction, that it's not very manifest. Okay, so let's see. Is this a good place to stop? Maybe I think I'll just stop there. That's probably a good place.
I already see one question.
Okay.
So for gravity, you can try and start with the action for the free field theory, Pauli Fiat, and a three-point vertex, and construct the whole of the action in this way. Is there something similar you can do here?
I mean, that is the spirit behind this construction as well. But I think implementing it in detail would be very difficult, much more difficult than in the spin 2 case. But what he uses is the gauge symmetry to guess what the full form would be. Just like if you knew the full diffeomorphism invariance and what are the objects like the Riemann tensor which transform covariantly under the diffeomorphisms, you could write down the Einstein equations directly. This is sort of the direct approach that he has taken, but I think in principle that's the claim, that it's more or less uniquely determined once you start from the cubic vertices onwards.
Any other questions?
At the beginning, you mentioned about consistent truncation condition.
The consistent truncation of the string theory to this?
Yeah. Can you explain?
As I said, it's what you might expect to happen, because on the field theory side, there is a consistent truncation in the sense that the OPEs, at least at tree level, what I mean to say is that the endpoint functions of these twist 2 operators are closed among themselves. So the operator algebra is closed amongst this set of twist 2 operators. So you would expect that is reflected in the bulk side in a truncation to just the fields dual to these, which are these higher spin fields. And so you might think that the full string theory has a consistent truncation, at least in the lambda equal to 0 limit, to these higher spin sector. And that's sort of suggested also by the fact that the Veselier construction is a unique construction which just needs only this set of fields. You don't need to introduce any new fields other than the sector. I mean, it was not at all obvious that there should have been a set of equations relating all these fields. And so it's highly non-trivial that it exists, because it's a huge diffeomorphism invariance, so it's not at all obvious, but given the fact that it exists, it's likely that it is what you would get from string theory if you were to restrict to this sector.
Can we also have this constant condition for massive case?
Constant?
This kind of constant condition for massive case, can you have constant condition, constant truncation?
Oh, consistent truncation
For
the massive case?
Yeah, massive case.
I don't believe there should be any consistent truncation, because once you have fields of twist higher than 2, I think you can generate, for very similar reasons like we had, algebraic. So if you take, say, phi cubed and phi cubed, I'll generate a phi to the 4th term in the operator product expansion, and so it will just cascade. It's very special to the twist 2 operators that they form a closed set. So I don't believe there's anything for the massive states. You have to include the full string spectrum.
Excuse me, what is the degeneracy of the states in the Vasiliev theory?
So there's one field
There is
of a given spin S, yes.
because in string theory you have an exponential growth.
Yeah. So this is one Rajesh trajectory.
Is one, just one?
One Rajesh trajectory. So you have one at every delta equal to, and so that's the sense in which it's much more than supergravity, but much less than string theory, and it has some of the big symmetries of string theory, at least some, maybe all.
Okay, no more questions. So let's thank Rajesh again for some very nice lecture.